Well, good evening, everybody. Welcome to Ellensburg, Washington, USA. The local time is 5:47 p.m. Here in the Pacific time zone. We'll begin our program at the top of the hour. About 12 minutes or so from now, 13 minutes maybe. That's my Swiss-German heritage. Gotta be on time. How are we doing tonight, everybody? Are we communicating? I see some comments. Hello, Patrick. Hello, Sela. Bunch of stuff that just rolled by. Thank you for chiming in all at once. It looks and sounds good. I always like to hear that. New Mexico, New York, New Zealand, Evelyn, age 7. Richard says it all sounds good. That's terrific. Sudbury, Ontario. Hello, Melissa. John's about to eat dinner. Colorado, 5x5. Excellent. I think I want to test something out with you for a second. This will be a different kind of an episode. Yeah, I'm going to test it out with you right now. So, can you help me here? We're going to test. So, this is a rock, and pretty dark, and not super satisfying as far as my view. It'll work, but not super pleased with it. So what I want to test with you is I have tried on occasion to use the back camera. In other words, I'm going to flip you around, and if this is a major step up, then I'm going to be, I think, going back and forth between the front of the camera, which you're looking at now, and the back of the camera, which is a different lens or whatever that can get in quite tight. So let's try this one more time. So here's the front of the camera. And we kind of lose it, right? So now let's go to the back. Now, to me, that looks remarkably better. Ideally, we'd be out in the sun right now, but isn't that much better? Good. I agree, Helen. I can get, well, I guess I can get too close, but that's pretty damn good. And, okay, well, for tonight, that's what we'll do. Tomorrow we'll be out in the sun, and we'll need it. We'll need the sun more tomorrow than we will tonight. Back is dark, yeah. Let me try something. I'm going to try something. I'm going to lift this ladder. Oh, shit. Hang on. Let's try it. Come on, you're coming with me. Nope. Well, I took you for your walk. You needed some fresh air. Yeah, the lighting's not ideal, but I got all these minerals laid out. I just don't have time to try to get set up. I mean, the weather just came through. We had a weather system come through. Otherwise, I would have been outside set up. But this will have to do. We can make it work. So it's 5:54. We will begin our program at 6 p.m. I got some thank yous I got to do, so I got to pick up the pace here for just a bit. So tonight we're talking about minerals. Tomorrow night come back for the second installment of Rock Week. Thursday night, 6 p.m. as well, sedimentary metamorphic rocks. Saturday and Sunday morning, 9 a.m., Milankovitch cycles, and thinking back to Mount St. Helens. Okay, I want to make sure I have time to thank some folks. So I saw a replay of, I think it was Saturday's live stream, where I was thanking Rachel and Justin from Monroe, who sent 2 6-packs of beers, dropped them off at the house. And everybody said German chocolate cake, and I didn't understand what that meant in the comments. And then it finally dawned on me that the Icicle Brewing Company, self-explanatory, favorite of Rachel's, actually is a German chocolate cake ale. So I've had one already. Rachel and Justin, thank you. I get the joke now. Didn't get it before. Thanks. This arrived this morning, a box from Nebraska. It's a book. From Glenn in Henderson, Nebraska. Glenn, thank you for the book. The Grand Canyon, Monument to an Ancient Earth. Can Noah's Flood explain the Grand Canyon? So Glenn had communicated with me by email and wondered if I'd be interested in reading a book. And it's like, okay, Noah's Flood, sure, send it on out. Well, I looked at it briefly, Glenn. I haven't had a chance to read the whole thing yet. It's a wonderful book, coffee table quality, and the whole goal is to look at geologic evidence for the Grand Canyon and realize that we're not talking about 6,000 years, but there is a way to have a spiritual background and yet embrace all this geologic time that we see in science. So I've never seen anybody do that, and the authors kind of worked together and put this together. So Very interesting book for a number of reasons. I will enjoy reading it. Thank you, Glenn. This arrived yesterday. I left it on the counter for Liz. It's very fancy, all-purpose flour from the Shepherd's Grain, certified sustainably grown wheat. And Gary Esser is a Moscow, Idaho grain producer. And Carl and Fred founded Shepherd's Grain in 2003. So I said, wow, Liz, I guess we're made of money, huh? The regular flour's not good enough for you? She's like, that's not my flour. So I had to email these folks and say, who sent the flour to me? And it turns out it's Karen from Tucson, Arizona, who has a connection to the industry here and the Palouse. So I was using all-purpose flour in that Palouse show. And Karen wanted to make sure I had enough flour, I think, or get me some good stuff. So 2 of these. Thank you, Karen from Tucson, Arizona. We will enjoy using it for our baking. And finally, Jeff from Vinman's Bakery, you gotta love it, rolled up outside 20 minutes ago and said, I got a call at noon today from Gene in Puyallup. Gene in Puyallup. And Gene called up the bakery and said, would you bake a dozen cookies and send it over to Nick? And Jeff threw in a bunch extra. So thank you, Gene from Puyallup. I have plans to use these cookies tomorrow night after thinking about it for 10 minutes. So I don't know if my willpower is good enough. We'll probably have to, well, Vinman's Bakery, you gotta love it. Thank you, Gene. Okay, I need to check with you one more time. We doing okay? Audio, visual, especially since I took you outside and screwed around out there. Am I doing okay? 5x5, we okay? And then I got to get rolling here. A few more I need to hear from you. Thank you. Thanks for joining us tonight. We'll get started in a minute. Framing's okay. Yeah. Hey, give me 2 more minutes, would you? All right. Okay. Whoop, whoop. Well, good evening, everybody. Welcome to Ellensburg, Washington, USA. This is my home here in town, and I'm so glad that you could join us this evening. We have a topic tonight that is unusual for us. If you've been with us thus far with our live streams, we've been telling stories about the geologic past. We've been using field evidence, whether it's out at the coast looking at tsunami deposits, or up in the Cascades looking at evidence of old volcanoes that no longer stand, to out in eastern Washington with the German chocolate cake and petrified forest horizons and ice age floods, etc. That's my wheelhouse. I love telling those stories. I love using field evidence to make sure that the stories aren't crazy, but they're bound in reality. We can actually go to some places in the flesh and actually see the evidence for these magnificent geologic stories from millions of years ago or thousands of years ago. Well, tonight is kind of a viewer request show, and in fact this week is a viewer request show. Quite a few of you have either emailed or left comments otherwise and said, how about you do just a basic identification show, like how can I identify quartz or feldspar or rhyolite, just basically Geology 101 type content. Geology 101 lab type content, to be specific. And ironically, that's what I've been teaching the most through the years. My first teaching job was fall of 1987, and my first job was teaching Geology 101 lab in Pocatello, Idaho, and I've pretty much taught about how to do basic rock and mineral identification every academic term since then. So I can kind of do this in my sleep. And oftentimes when I teach those basic skills, I kind of get sleepy myself, to be honest, because there's no real payoff. There's no immediate payoff to learn these specific skills, except simply to label things. And if you know these programs, you know I'm not a fan of just labeling things. That's not the goal. I think for a lot of people, science is viewed that way. You study something and then you name it and then job well done. Well, I wouldn't be in science if that was the game. The game is the game is solving unsolved mysteries. The game is being a detective. The game is involving travel to beautiful places. The game, geology, is using human history and intersections of humans and natural systems, as we've been doing for all these live streams. So that's a preamble saying that our goals are very different tonight and our procedure is very different tonight. There is no cozy fort tonight. There is no guest walking in the front door. There are no maps. There's no video clips taking us to particular places. Our goal tonight is to try to look at some mineral samples and identify them. And if we have 3 of these sessions, and we do, tonight is Tuesday night, 6 p.m., tomorrow night, Wednesday night, 6 p.m., Thursday night, 6 p.m. We'll do 3 of these in a row, and we need to have them work together. So you ready? Here's the first message. Muffler boy. Rocks and minerals are not the same thing. I drew a picture of a rock. Isn't it pretty? Looks like Christmas time. What am I doing? Am I super bored? Kinda was this afternoon. But why did I draw this picture this way? Rocks are composed of different kinds of minerals. Rocks and minerals are not the same thing. This is a rock, but each of these individual colors is a mineral. And you're like, well, hold on, let me stop you right now. That doesn't jive with what I know about minerals. This is you talking now. Because I have a mineral in my den. Let me show it to you. And you're like, this is a mineral, isn't it? Isn't this a mineral? I thought you said, rocks, these things you hold in your hand, are rocks and they're made out of minerals, but I'm holding this thing and this is a rock, isn't it? Or is it? And the answer is, if you have these things called crystals, and of course this is a quartz crystal, you can get lots of healing power. Lots of healing power from the details of this quartz crystal. There are 6 sides on this quartz crystal, and those 6 sides decide to come to a point. And there's some very specific geometry. Hello, you want another one? Everybody loves a good crystal, right? Actually, So we're just still doing the first step, realizing that there's a difference between rocks and minerals. You know what? No, I want to do this. So if I drew this picture and I'm making this point, which I made quickly, but I'm going to do it again. Rock, singular, made up of a bunch of different little colored specks inside of it. This is what minerals usually look like in nature. Minerals in nature usually look small, and they look a bunch of different colors that are inside of rocks. Before we go to the crystals, let me show you some examples of this. I'll even keep holding this up for you. Okay, rock composed of different minerals. Okay, I'm holding a rock, but in this case I got a bunch of visible minerals that are white and have a very specific shape to them. And then there's all this black stuff, but you'll have to take my word for it because I don't have a microscope for you right now. If we would cut this rock open, make it paper thin, do something called a thin section, we would see that this black area, all that black area of this rock is made up of a bunch of microscopic minerals of different shapes and different colors. You want another example? All we're doing so far, before we get into the details of mineral identification, is understanding firmly that there's a difference between rocks and minerals. And almost always, minerals are small specks inside of rocks. I'm holding a rock. You can see different kinds of minerals. Why not? Let's show off the camera. Flip. I don't know if this light is helping or not. That light's kind of too artificial for my... That's better. Screw the light. Okay, so there's some black minerals, there's some white minerals, there's some gray minerals. Again, this is the common experience when dealing with minerals. So it's confusing because when you go to a natural history museum, and they're a good museum, and they have minerals on display, they're not showing you this, are they? They're not showing you the teeny tiny minerals. Ah yes, walkers under the age of 30 who scream at the top of their lungs as they talk to each other walking up the sidewalk. What is going on, young people? Why do we have one volume at all times? She's bothered by. So this is a mineral called fluorite. You really only see fluorite in crystal form. I know of no rocks that are composed of the mineral fluorite. Beautiful, wouldn't you say? So if minerals are usually these tiny specks inside of rocks, why do we even have these things? They're rare, for sure. You need a rare circumstance to allow these things to grow nice and big. Here's another one. Quartz crystal that's big. This is a different one that I showed you before. And then there's a bunch of small guys as well. I can come in pretty close now, can't I? Ooh, this looks like rock candy. Ooh, maybe I should try to eat this. Wouldn't that taste good? Just take a big old bite off of that. Okay, I think you know the answer to this. To get these crystals, we need space. It's a space game. And in a magma chamber, which is the topic of tomorrow night when we talk about igneous rocks, in a magma chamber, there is absolutely fierce competition for space. And believe me, if each of these minerals had the chance, had the room to stretch out and grow to a crystal form, to crystal habit, they would do so. They would love to have had the chance to do this. But again, you're hearing my message. Almost always, there's no room for those minerals to grow, and so they're kind of these stunted little versions of themselves, making up different kinds of igneous rocks. So when you have an old school handbook, and I've got a couple that people have gifted me over the years, which I'm grateful for. I don't know, how old are you? Do you know books like this? Before the internet, this is how you kind of, maybe even still today. This is a golden field guide, minerals of the world. Unfortunately, it's usually people that pass away and then they're like, I don't know what to do with all this stuff. My husband's got a whole basement full of this. Would you be interested in having any of this stuff? So a lot of the samples that I have or books that I have are old. This is from 1973. And my point is they're showing us these crystals, these rare situations where the minerals grow nice and big. Or here. But you're hearing my major point, I believe. So you're going to get a little lesson, and I am starting, I promise, with the actual procedure in just a second. You're getting a message from me tonight about how to identify common rock-forming minerals. Because my whole game with this lab, I'm talking to you now like you're in my lab, okay? The whole approach to this lab is we're going outside. We're going outside for our 2-hour field trips, and we're going to the Yakima River, we're going up on Menashtash Ridge, we're going up by Thorpe, and we need to know our minerals to make sense of what's going on out there. But you're not going to be looking for these huge crystals. They're not out there, I'm afraid. But we're going to break open rocks and identify the minerals in the rocks, and therefore we can identify the rocks. So to understand how to identify rocks, we need to know how to identify minerals first, but we're not working with the showy minerals. And before you click off, since we're not working with different kinds of crystals around the world, I do have a few more for you. Speaking of guys in their basements with a lot of spare time, maybe after they retired from the electric company and want to stay out of trouble. So, here's Jerry, let's say. So Jerry decides, well, I'm going to go to all the rock and mineral shows I can find. I'm going to buy this piece of pyrite, this fool's gold, and then I'm going to have some fun. So this was donated from a widow. I'm making up the name Jerry. I don't remember who donated. If you happen to be watching and you actually donated to the department, thank you. Students always enjoy looking very carefully at pyrite. But here we are again. Crystal form, crystal habit. This looks like gold, but it's fool's gold. It's pyrite. Okay. I feel like I want to get into the guts of the lesson, and hopefully you feel like you want to do that too. So we're going to just go right through my normal routine now, identifying common rock-forming minerals, and this will help us tomorrow night and the next night when we start talking about different kinds of rocks. Okay? Great. So, this is the geology lab manual that we use, that I put together a long time ago. And we use it every quarter. You can see how many lab sessions we normally have. There's 20 students in every one of the labs. I always teach the first lab of the week, and then my graduate students kind of sit and see what I'm doing, and then they kind of replicate it. And here's our field trip sites, by the way. Okay, so week one is not the mineral thing. Week one, we try to learn some map stuff and some basic reasoning stuff, and we get out in the field right away. But when we get serious about identifying minerals, this is my approach. So, I don't know if you have ever taken a geology class in college or high school maybe. It's kind of unimaginative. You're given these little boxes, and they've got these mineral samples inside. And your job is to identify what the mineral is using some sort of process. And so here's the process that I use. Determine the color, determine the hardness, determine the cleavage, and then come up with the mineral name. And that's what we're going to do right now. And I think once I roll through that and show you a bunch of examples, then I think I'll go right to the live Q&A, and we'll see where you want to go with this. You probably had some preconceived notions or answers that you wanted, and I don't know if what I'm doing tonight is a surprise for you or not. But that is what I'm doing. So, we're not going to the rocks yet, but we're going to look at samples of minerals that are bigger than normal and look at them and carefully study them and try to identify them in bigger than normal size so that we can be ready for their more common look inside of rocks tomorrow night. Okay? So you're holding an unknown mineral in your hand. And you know what? I don't know, it was 3 weeks ago. I tried doing something in the live stream where I said, if you know the answer, don't type it in so that kids and other people that don't know can kind of, really try to vote. Oh, that was a train wreck. Everybody wants to say they know what the answer is. So I'm not even going to try that, okay? So I'm sure you'll just be Johnny right on the mark if you see this and you know what it is. And if that makes you feel good to type it out, then go for it. I want you to feel good. So here's our first unknown sample. And, it's common for students to put their hand up and I need help. It's like, okay. And I don't know what this rock is. And I want to say, it's not a rock. It's a mineral. There's a difference. Didn't you just hear what I said? It's not a rock, it's a mineral. And they go, whatever, bro, just, I need some help. So here's more of them. So there's a, what sample is this here? Sample number 1. Good place to start. So our goal here is these are all the same mineral, say it with me, mineral. And they're bigger than normal. I mean, they're not super big crystals necessarily, but again, these are not tiny little things, are they? In fact, you know what? Total experimental, by the way, tonight, if you haven't figured that out already. Pretty choppy, but hopefully you're kind of having fun with the kind of spontaneity of it all. And when I get spontaneous, that's not a word, I sneeze. No, I don't. Maybe I'm going to. So just to drive the point home even further, here's a rock that has a bunch of mineral number 1 inside of it. But here's our mineral number 1 in a bigger than usual form. Let's do that out the back. There's the rock that has pink stuff, black stuff, gray stuff. We don't know those minerals. We certainly don't know this rock yet. But again, I'm picking for this lab, even this one here. So this is the mineral. This is the rock. You can see why the student would say, I don't know what this rock is. Help me with this rock. It's not a frickin' rock, man. And minerals always have one color. I mean, this is a rock because there's different colors inside. There's different constituents inside of this. It's almost like a cookie where you have different kinds of things inside of this cookie. This is a mineral. It's just got one scene. So maybe you've already typed in what you think this is. And if you have, good for you, but I don't know, maybe you're wrong. So what's the process? And how can you kind of work through this on your own, lab student? I've given you all these little boxes with unknown minerals inside. How you're supposed to kind of do this on your own. It's a hands-on lab. Well, here's our three things: color, hardness, cleavage. In the lab manual, and every lab manual has a different approach, so if you were taught a different way, that's fine. This is my approach. This is page 16 in my hymnal here. So this is the mineral identification key. We're not talking about rocks, we're talking about minerals. We're going to work through, I don't know, I think about 6 samples here. 6 common rock-forming minerals, and we're going to use this key. The first question was color, and we have to decide, do we have a dark-colored mineral or a light-colored mineral? And our rule in our Geology 101 labs, is it a black or green mineral? Then it's dark. Anything else, we're going to call it a light-colored mineral. Okay? That's my approach. So, I don't know. Are these guys black or green? They are not. So therefore, we're going to ignore this part of the chart, and we're going to look at this part of the chart. You can see there's actually mineral names over here. So if you've already typed in your answer for sample number 1 and you don't see it over here, it's time to get nervous. I don't know why I'm confrontational tonight. Okay, so we're in the light-colored mineral area. Second question, what was the second one? Hardness. Now, there's over 2,000 minerals in nature. Most of them are not common rock-forming minerals. But all of those minerals have been assigned a hardness on a hardness scale that goes from 1 to 10. It's called Mohs hardness scale. Sounds like I'm making that up. M-O-H. There must have been a guy named Mo. I'm sure some of you will type it in somehow. Okay, so in the hardness scale, we go from 1 to 10 on the scale. What's the hardest mineral in nature? Diamond. Diamonds are the hardest minerals in nature. What's the softest mineral in nature? It's a mineral called talc, used to make talcum powder, baby powder. So every mineral in nature has been assigned a number between 1 and 10 on this scale, and the higher the number, the harder it is. And by testing the hardness of this unknown mineral, like number 1, which we're about to do, will give us some information on how to identify the mineral. Well, it turns out that glass, natural occurring glass or artificial glass, like in the windows behind me or the glass that's here, has a hardness of 5.5 on this 1 to 10 scale. So this is also still pretty much grade school here. We're going to perform a little hardness test. We don't know what sample number 1 is, but we can perform a hardness test using glass. All right, now you can order your lab supplies from Ward's or some other supply company in North America at least, and you get little things like this that are very difficult to get your hands on, and it's super safe and all that, but I've never been satisfied with these. Plus, you got like 1/4's worth of students. I grabbed these from the lab today, and you're already all scratched up. And even though they're 19 or 20, it is grade school. They're like writing their name with them. So for years and years, I would always bring in Planters peanut jars. I'm a big fan. This episode of Nick from Home brought to you by Planters Peanuts. You gotta love them. Because for years and years, at least here in Ellensburg, those Planters peanut jars were made out of glass, and they were a nice tough glass, and it was just the right, you know, the jar was just perfect to hold. And I'd wash out our old peanut jars, bring them in for 25 years. And then there was a sad day here, I don't know, 10 years ago maybe. It's all plastic now. So Liz just said, I'm going to Super One. You need anything? I'm like, yeah, could you find a glass jar somehow that's thick enough where I'm not going to break it for mineral ID? And she's like, well, why don't you go down to the fruit cellar and get one of our mason jars? I'm like, you're going to give me permission? I can scratch one of those up? Oh, yeah. Really? Just double checking. I'm not going to be in trouble if I do that. No problem. So this may come up in June, or I guess August. But for now, you have verification. I can show her this. You said it was okay. So, mason jar, made out of glass. Pickles, used last time. Am I moving too slow for you? I don't care. So here's our unknown sample. I want to know, is this mineral a 3 on the hardness scale, a 7 on the hardness scale, a 10 on the, is this a diamond? All right, so I know this is 5.5 on the scale, so I'm going to do this. I'm going to do it close enough so you can maybe hear it. First of all, you can hear that? Okay. You can kind of hear it digging into the glass. I don't know, can I do it for you while I'm holding this? Okay? Oh, these jars are pretty stubborn. You can hear it and you can see it. And our unknown sample is hard enough to cut glass. So what's the hardness? It's got to be a number bigger than 5.5. Okay, we still don't know the name of the mineral, but we have information. Okay, let's go back to page 16. We know we have a light colored mineral. Now we can see that I've got a group that are harder than glass and a group that's smaller than glass, softer than glass. We decided our mineral, number 1, was harder than glass. I just showed you that. So now we're down to one of these 6 choices. These are the answers over here. We're not done, but we know we're down to 5 choices. This is like identifying trees or something, right? And have you ever done that? Using an identification key, and you count the lobes and your shapes and the veins and the, I don't know what I'm talking about, but you figured that out already. Okay, this is pretty easy so far. The last question, the last task is actually difficult. It involves cleavage. So, quick geometry lesson. Geometry review from middle school or high school. This is a box. This episode of Nick from Home brought to you by Arm & Hammer Baking Soda. Arm & Hammer Baking Soda. How many sides on this box? How many sides? 6? 1, 2, 3, 4, 5, 6 sides. What's the angle between the sides? 90 degrees? 90-degree corners? Right? Perpendicular corners? Good. Harder question. How many geometric planes run through this box? And I'll wait for this one. I'll wait for your comments. Don't be afraid now. You're in a safe, nurturing, warm environment. There's no reason to feel foolish. How many geometric planes run through this box? P-L-A-N-E. 3, 3, 3, 6, 3, 3. There's 3. The answer is 3. And here's how that works if you forget what a plane is. A plane is an orientation in space. This is a plane. I'm on one geometric plane. So if I have one and another, I have 2 sides, and they're parallel to each other. Those are two sides, but they're in the same plane. Can you see it now? So I have top and bottom, that's one geometric plane. Two sides, that's a second geometric plane. Front and back, that's a third geometric plane. Do you see it now? There's 6 sides, but there's 3 planes. 3 orientations. Okay, what are we doing? Why are we doing this? Well, this cleavage information we're going to do with our unknown sample. And cleavage is by far the most reliable way to identify minerals. So the most common mistake, if you're a rookie at this, is to memorize a color. Obviously, we quiz our students. So the next week I say, hey, you know, where's I said, you know, you're my student now. Okay, so you got to work through 12 of the minerals. Come up with, do your work, fill out all your work. I'll show you the worksheet. I say you've got an hour and a half to fill out. Here's all your samples, and you're going to fill out your boxes. You see what the prompts are here. It's just what we're doing. And then put down your names, and then I want to check your answers before you leave the room. Make sure you did the right work. And then when you come in next week, first thing we're going to do is I'm going to quiz you. And I'm going to give you 4 minerals that I'm not going to tell you what the name is. And you're not going to be able to use your chart like you're using now. You're going to have to learn how to identify these things. And then we'll do the quiz, and then we'll go out and go to the field in real time. So my point is, the cleavage thing is crucial. And the problem is, the students oftentimes say, oh, it's cleavage, that's weird. I'm going to blow that off. I don't even get the angles thing anyway. I'll just memorize a color. Well, here's why that's a problem. Do you remember that fluorite crystal that I showed you? This is where he looks. So this is that beautiful, this is not a common rock-forming mineral, but I'm showing this to you as this is a color for fluorite. And if you're a rookie student, you go, okay, deep purple, like music, like my grandpa loved deep purple. Okay, right, okay, I got it. And then you're like, oh, crud. So this is fluorite? Well, this isn't deep purple, but it's got a little purple in it. So maybe if I just memorize purple, I'll be good. And then you're like, oh, all these are fluorite. Memorizing a color will get you into trouble if you're trying to do well on a minerals quiz. Color is variable. Color involves physics and chemistry that I do not understand. I'll save you the trouble. I don't understand. It was taught to me long ago. I've promptly forgotten it. But the point is, the cleavage information is always the same with a particular mineral. And you don't even know how that works, but I'm about to show you. But the color, not reliable. Let's not memorize color. Okay, we're still in the process of trying to identify what this pinkish mineral is. Orangish, tannish mineral. I mean, I used to call it flesh-colored, but not all of us have the same color flesh. Things have changed for the good in that respect, as far as the way we speak. Another little look tomorrow night. Here's a rock that's loaded in our mineral number 1. They're extraordinarily large, but there they are. They're showing up in rocks occasionally, but we're not there yet. So you remember where we were. 6 sides, 90-degree angle between the sides on this baking soda box, but only 3 geometric planes, correct? Now, we need to decide, especially if you look out the back of the camera, Do we think this mineral has cleavage or not? Do we think this mineral has cleavage or not? And you're like, I don't know, did you tell us what cleavage was? Like, I know what cleavage is, but like geology cleavage? Did you actually tell us? The answer is no, but I'm about to tell you right now. If you are a mineral that has cleavage, you break along perfect planes. If you take a mineral that has cleavage, you take a hammer. I almost want to do it right now for you. Should I? Why not? You're worth it. I've got a broom. I can clean things up. 6:37. I got to pick up the pace. So this is a mineral. So we're going to get back to number one, I promise. But this is a mineral, and it's cubic. There are 3 planes. It's almost like it's exactly like the box, isn't it? This is not a common rock-forming mineral, but it is a mineral, and it's got a top and bottom. That's one plane. It's got 2 sides. That's a second plane. It's got the other 2 sides. That's a third plane. And even though it looks a little funky here, and there's some broken corners, you have to take my word for it. Yes, it looks like an ice cube, Matt. It's not. What am I tasting? This is salt. This is halite. This is the mineral halite. And it has good cleavage. And I'm going to break it, man. I'm going to break it right in front of your eyes. I hope I don't send a shrapnel of halite into my camera or my face, more importantly, my camera. But I want to show you the importance of cleavage, because I'm saying if this is a mineral that has cleavage, and it does, we can tell it has cleavage by its shape. It's not an accident that it's cubic, but more to the point, if I break it, it's going to break along interior planes that mimic the surfaces. I got to do it. Ready? It's a nice sample. I hope I don't break it so the whole thing I'll just try to do a little corner here. And I got to hold it for you so you can see it. I'm going to be back just a little bit. Do you know what I'm going to try to show you? I'm going to show you that the little baby pieces that I break off are going to be cute little ice cubes as well. Because there's internal structure with 3 dimensions at 90-degree corners. Let's do it. Pretty good. Okay. I lost a corner. Oh, this is sweet, man. This is totally worth it. I've hung on for dear life. And now I'll even do it on the backside. Oh, I got people making fun of me. Don't ruin the sample. Screw you. I'm teaching. Oh, yeah. Oh, yeah. And even, oh, this is nice. You can even kind of see some of the internal planes running perpendicular in another direction. I got two nice big samples that we can still use in the lab. I'm very pleased with that. And if you're scolding me, I'm not a fan of you right now. But I got to find a couple of the babies. The babies fell on the ground, and this is true cleavage now. So we'll be able to see the babies. It's like, oh, they'll be like little broken things. No, they won't. They'll be perfect little cubes too. They'll have 3 cleavage planes intersecting at 90 degrees. I'll be right back. Oh, there's even, hang on. You know why I'm so pleased? This is 30 years of saying, if I took a hammer and broke this right now, it would break into a bunch of small pieces with the same shape, but I've never done it in 30 years because we have a limited amount of samples. But we got almost 1,000 people watching, man. It's worth it. Okay, I picked up 3 babies, 1 brother and 2 truly infants. That guy. Wow, wow, wow. Wow, wow, wow. Let's get the babies. Oh, the babies. The babies. Oh, he's so cute. He looks like his mother. Oh, that's so cute. 3 cleavage planes, 90-degree corners. WTF. You must be new to us. Maybe you should go back to where you came from. Let's finish our program. I definitely do not want to break sample number 1. There's not that many of them that we have in the lab, and they actually cost quite a bit when you order them from supply companies. But what are we going to do now? We're going to count the cleavage planes. And by doing that, we're actually going to count the surfaces that actually reflect light. That reflect light. There we go. So we're looking at a cleavage surface because when we look at it and rotate it, it acts just like a mirror. There's just one position where the whole surface lights up, and then if we go just a little bit more, it goes away, right? So that's a cleavage surface. Let's flip it over. We got the same mirror reflection there. Can you see it? So that's one cleavage plane. The top and the bottom are parallel to each other, and they both do that mirror reflection. That's one. Now, let's go to this. So that was top and bottom, right? Yes. Let's go to this one now. Does it reflect light? Yes, it does. So now we have a second cleavage plane. Let's go to the other side. Uh-oh, this is Mother Nature now. Things are kind of irregular, but we can still see the mirror reflection, correct? So that's a second cleavage plane. Are you keeping track? I'm about to drop this. My left hand is starting to cramp up. I got one cleavage plane. I got another cleavage plane, those two surfaces. Now let's go to the other two. Nothing. Mwah, mwah. I don't see any reflection there. So there are not three planes. There are two planes. That level of detail of getting down to looking at surfaces that reflect light and those that don't give us two cleavage planes that intersect at 90 degrees. Light-colored mineral, harder than glass, cleavage is prominent. In other words, if the mineral, I'm not going to do it. Quartz never has cleavage. So if I take a hammer to quartz and I wail on it, it's just going to shatter. Just like a beer bottle off the end of the bar. It's just going to shatter into a million pieces, and every little baby piece is going to be a different shape. It's not going to have cleavage. But because of these mirror reflections, we have cleavage prominent, and so we're definitely talking about one of these feldspars. Oh, I still do have flesh colored. Plagioclase feldspar is white to gray. Potassium feldspar is flesh colored to pink. Both have two cleavage planes at 90 degrees, and the hardness is 6, which checks out. So the answer to number 1 is potassium feldspar, sometimes called K-spar. K is a chemical abbreviation for potassium. Okay? So, this is a rock that has a lot of potassium feldspar, big old dominoes of potassium feldspar. This is from tomorrow night, but this is a pink granite. Why is it pink? It's got a bunch of potassium feldspar inside of it. Make sense to you now? What does plagioclase feldspar look like? It's a feldspar, so it's going to have everything the same that we just did. Light colored, harder than glass, cleavage prominent, 2 cleavage planes, 90 degrees, the flashing mirror, the whole thing. But plagioclase feldspar looks slightly different. It's kind of a white to gray version of what we just looked at. This is plagioclase feldspar. It's got kind of a wood grain look. Okay, actually, both feldspars kind of have that wood grain look. You can see the flash of light. So cleavage is definitely part of the story. These two ends are not going to have the flash. And for those more advanced students, can I maybe get this? Sometimes plagioclase feldspar, depending on the quality, have striations on them. They look like little fingernail scratches when you get the surface to light up. Not great. Maybe you can see a hint of some fingernail scratches on that mirror surface coming at you. Not as good as it could be. Okay, so it's almost 7 o'clock. So I want to that's the process. And we could go through each mineral sample using that process, but we're not going to do that. We don't have enough time. And I want to get to your questions besides. So let me just do a little show and tell then for you with other common rock-forming minerals that we use in our lab. So you just saw plagioclase feldspar. You've seen potassium feldspar. Hey! Another geologist walking by, Susan Kaspari. We should get her. We should do ice core stuff with her. So this is more for tomorrow night, but there's lots of black minerals that are insides of rocks, and by far the most 2 common black rock-forming minerals are either hornblende or biotite. So let's flip around. Hornblende. Do you think hornblende has cleavage? Yes or no? Now remember, they're not made in a factory. They're made in Mother Nature, so they're not going to be as perfect as what we had before. This is hornblende, a very common black rock-forming mineral that we'll use tomorrow night. It's part of the amphibole family. The answer is yes. Hornblende has 2 cleavage planes at 60 degrees to each other. So again, if I broke this hornblende, you know what? I got a bigger one. It's tough to get a good sample of big hornblende. You have to pay quite a bit. But I like this one. Oh, you can see it. Look at that. You can see the mirror reflection, can't you? So this is not a rock. This is not a rock. This is a mineral. And you can definitely see the mirror reflection here. That's a cleavage plane. You can kind of, hopefully you get a sense that there's 2 cleavage planes here. Hornblende. Now biotite only has one cleavage plane, and that's why biotites are very famous for being so flat and sheet-like. And you're like, does this really exist in nature? Like, why would something like this be tens of millions of years old and survive? And the answer is, instead of biotite in nature just being a bunch of these little flakes, I mean, look at how delicate some of these flakes are. This is what's known as a book of biotite. So I don't know, maybe you've been hiking in the mountains, maybe you've walked right by what you just thought was a rock, but it turns out it's a book of biotite. And you can kind of get the sense that you could take a hammer to this, which I'm not going to, this is a very valuable sample, and it's just millions, maybe thousands of sheets of this very fragile biotite. I'm going to finish my show and tell because I brought a lot of stuff home from school for you, and then we'll go to you. There's a white mica called muscovite, also very delicate, perfect one cleavage plane direction. So the less intelligent students will raise their hand and say, how many cleavage planes here? And I'm like, how many do you think? They're like, 14? I'm like, 1. Oh, okay, 1. Now you might be surprised we haven't talked a lot about quartz tonight, except in crystal form. But you'll see why tomorrow, I think. But remember, quartz never has cleavage. So here's rose quartz that doesn't quite look as pink. It doesn't have a natural. This is kind of a pink look to rose quartz. And even by looking at this, maybe you can see that there's no cleavage here. If I break this, it would just shatter. Same with this, which is some smoky quartz. You can see why it's called smoky quartz. There's different amounts of translucency inside. Quartz is by far the most common rock-forming mineral and will be a major help to us the next couple of nights. 5 more minutes? What's this? It's a mineral. I'm now just into cool show and tell. It's got 12 sides on it. That's correct. This is a garnet. I don't like that light. It's got a kind of a ruby sample, ruby color. And so here's a garnet out by itself. And here's garnets that are inside of a rock, a metamorphic rock called garnet schist. We'll talk about this again on Thursday night. This is very rare, of course, but there are some garnet schists in our county, in Kittitas County where I live. Any idea? Not quartz. It's got these are crystals, but they don't have the same geometries as the quartz crystals. This is topaz. Some of you guessed olivine. Let me show you. Olivine has the same kind of blobby look as quartz does. This is topaz. You're not looking at quartz, you're not looking at olivine. Let me show you a olivine. The olivine is more exciting in a basalt than it is just by itself. When you order an olivine from a mineral company, they send you stuff like this, and you're like, oh, I don't know. I guess it's olive green in color, but not as exciting as I was hoping for. Got a couple more for you. Actually, I got a test for you. This is new. We haven't looked at this yet. This is a mineral that's not a common rock-forming mineral. Does it have cleavage? I'm not even going to turn the light on because I like the light better this way. Cleavage, yes or no? The answer is yes. You can see some mirror reflection, I think, right there, can't you? How many cleavage planes? The answer is 3. And what's the angle between the cleavage planes here? This is not a perfect cube, is it? What would you eyeball as the angle here between these planes? And again, the comments are delayed here, so I'm not getting what you're saying in real time. The answer is 75 degrees. Every corner here is 75 degrees. Can you kind of see it now? So this is a very specific mineral that's quite soft. And if you're really desperate to identify what this is, you got to trust me, 75-degree corners. This is hydrochloric acid, which is mostly water, but it has a little bit of HCl in it. In other words, acid that will kind of eat into your clothes a little bit. I'm going to try to do this blind. I'm looking at it, but it's on the other side of the camera from me. But I think this will work, especially if I don't let the bubble. I'm just going to try to do 1 drop. Do you know what's going to happen? There's a chemical reaction between the hydrochloric acid and the calcium in the mineral called calcite. So this will help us on Thursday night as well. Calcite. Two more and I'm done. This is gypsum. This is the mineral gypsum. It's very soft. It has 1 perfect cleavage. You can see that mirror reflection pretty easily. I could easily break this, or I can easily make a scratch with my fingernail on this. And then here's galena, very heavy, metallic. And I tend not to use streak. But streak is another way to identify minerals. Okay, well, we have record-breaking numbers of folks tuning in tonight. I'm very surprised. I guess that's the power of just the actual raw materials that we have in geology. And that's a lesson for me. I love so much other stuff that I rarely get down to this level. But of course, if I'm standing and lecturing to 700 people in an auditorium, I can't just go, see, there's mirror, you know. So there are some advantages for this format. It's a very intimate relationship. It's a very intimate relationship that you and I have. Okay, I got to make some room for my laptop so I can read your questions. I probably have a few more other samples that I just don't see right now, but it's 7 o'clock. It's time for me to respond to you. We'll get this yellow light off. Hope you enjoyed that. We'll do something similar tomorrow night with igneous rocks and cookies. Okay, I'm clicking over to live chat. I'm scrolling back. If you're new to us, uppercase is the best way for me to see your question, especially children's questions, but of course, I'll try to answer as many questions as I can. Let me go back. Yeah. I need a disclaimer. I'm very weak on mineralogy and crystal chemistry. I was literally taught it 40 years ago, and that was in days where you had index cards, you're memorizing chemical formulas of whatever, and then you move on. Not taught very imaginatively. So I'll do my best, but I'm not going to have the detail you want probably with some of these questions. Evelyn, age 7, have you memorized that identification chart, or do I still use it? Well, Evelyn, I have memorized it just because I've taught it so much. And there's not that many words on the chart. And oftentimes when a student says, well, how am I supposed to memorize all this for next week? I'm like, look, you've just got the dozen samples. I'm not going to quiz you on a sample you haven't seen. So let's just think about what's valuable for each of these samples. So I'll give you an example, Evelyn. Oh, you got a black mineral? Well, it's either hornblende or biotite, and we can tell the difference because of the angle between the cleavage planes and the number of cleavage planes. You've got a pink mineral, that's more tomorrow. So it's a couple of key features for each mineral, and that's what I remember, Evelyn, instead of memorizing thousands of words. I couldn't do that. Could you? Evelyn, I couldn't memorize thousands of words. I can barely remember my name every other Tuesday. How do I tell real gold from iron pyrite? Well, Eric, I'm sure there's a crystal answer for that. In other words, a geometry, the way that pyrite looks. Where did that go? So one way to answer your question is this is not real gold because it's in these crystals are in this shape. And if you did not join us for our Liberty Gold live stream back when it was freezing, and that was like 2 months ago, we've been doing it that long, Rob Reppin was showing us his crystalline wire gold, and it didn't have this shape. So that's an easy answer from that point of view. Also, of course, gold is very rare, and if you see a bunch of this stuff in one place, then it's probably not real gold. But it's often comes down to the geometries, and that's what I've been trying to emphasize tonight. Does the location where the mineral is found aid in its identification? Yeah, yes, sir, yes, ma'am. I think I mentioned this before. When somebody just brings a rock in off the street and they want help identifying it, my first question is always, where did you collect it? Because if I know the basics of the bedrock geology of the area, I can eliminate a bunch of dumb answers. And then I can think about the half dozen of reasonable answers and start looking for details. And the same is true for minerals. Same is true for minerals. Tommy, what's my favorite mineral and why? Do I have a favorite mineral? I think it's potassium feldspar. We'll use potassium feldspar quite a bit tomorrow night. It's a handsome mineral. It has beautiful cleavage. I love beautiful cleavage. I like the geometry of it, and I like how easy it is to identify in rocks. So I think that's why it's my favorite, Tommy. When you grow salt crystals, do they have the same cleavage? I believe so, Jack. I've never done that. I've never grown my own salt crystals. But yes, 90-degree cubes. 90-degree angles between the cleavage planes. I went all the way down to the bottom for my usual. Here we go. Here. Whoa, 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 whoa. My field guide talks about twinning as part of identifying minerals. What does that mean? I'm not really sure, Yelly. Twinning, I only know twinning with certain feldspars. There's a certain kind of mirror set, or sometimes there's some things you can see on the surface of plagioclase feldspar cleavage planes. There's something else with twinning that I forget. But if twinning is used with other kinds of minerals besides feldspar, I'm unaware of what they mean. Can every mineral be identified by your sheet that you shared? Thank you, Jason. Not really. Well, yes, a much more elaborate system than I have. Again, I will use botany. If you've ever keyed out a tree, there's all these different options based on all these things you're observing, and you'll finally get to the answer. There are very elaborate identification keys for minerals that take all of these common rock-forming minerals, but also very rare minerals, and you can kind of work that through. But as you heard me, I'm really teaching my students how to identify 12 minerals. Because my gimmick is, I actually say this, and I think it's helpful. You're in my lab, we're going to do some classroom labs. Every piece of work we do in this lab is going to help us in the field. Like, we're learning these details to then apply them out in Mother Nature. And I don't know about for you, but for me as a student, I got bored to tears and even kind of rejecting the professor sometimes, kind of in a snobby way. I just kept saying, I guess not out loud, I don't care if it's in chapter 3. That's the whole reason we're doing this, just because it's in chapter 3? I wanted to say, please help me see how I could possibly use this in the real world. If not, what are we doing here? And that was a way that things were taught back then, perhaps still are in some cases. I feel like the whole thing about teaching, especially when you're down in the weeds with a bunch of details and what's the angle and all this, that's super valuable if there's a point. If you're like an apprentice and you're learning your tools before you go out and do the job. So that's how I have chosen to kind of couch much of this. And that's why a session like this always feels kind of empty for me, even though we have lots of people watching. There's no payoff immediately. I like the payoff. Why don't you use streak? I guess just time, James. I didn't even bring one in. The streak is like, can you picture like a porcelain plate? Like a tile from a bathroom, but kind of a rough side, not a polished side. And there are especially metallic minerals like the galena or hematite or pyrite. And it's got a certain color, but then you drag it on a streak plate and you look at the color of the kind of skid mark that it left. And that's another way to help identify. But since I don't choose to teach a lot of metallic minerals, I don't have a use for streak plates. Again, based on the rocks that are available here in the valley, where we're doing our field trips. Would opal be a mineral? Yeah, Tanya. Opal is basically it's another name for quartz. There's so many different forms of quartz and different names for quartz. Chalcedony, cryptocrystalline quartz. We'll talk a little bit more about quartz in an igneous rock sense tomorrow. But yeah, and gems are part of this world that I don't know much about, but maybe your interest in minerals is more of a gem or jewelry type of a thing. That's just not me. My folks have a very large granitic erratic west of Edmonton. What mineral gave it a bluish color? I've never heard of a granite that has a bluish color, Terry, and so I wonder if it's granite. And you say it's granitic. The only real blue minerals I know are metamorphic minerals, high temperature, high pressure metamorphic minerals. So maybe we can weave that in Thursday night when we talk about metamorphic rocks. Can I explain the difference between igneous and metamorphic rocks? Hang on, Matt, Thursday night and tomorrow night. This is minerals only tonight. Explain topaz again. I don't remember much about topaz except it's an interesting shape. It's a mineral that's not common for rock forming, and so if you Google topaz, you'll learn a lot more than I can tell you right now. I did go hunting for topaz once when I was altered. Long story. But you go out in the deserts of Utah and you have a screwdriver and you dig into this kind of crumbly volcanic material, and you can pull out these beautiful topaz crystals. Muffler Man across the street, thank God. Chemical makeup like SiO2, yes, quartz is nothing but silicon and oxygen. And every one of these minerals has a long string of elements in it, and that's where the chemistry comes in. When you take a mineralogy class at a university, it's mostly chemistry, crystal chemistry, and you're learning different arrangements of elements, different silica tetrahedrons, and that ultimately there's chemistry and organization of these atomic structures that explains these different angles between the cleavage planes. Age 8, my daughter wants to know if you have a diamond sample. We're both teachers. We don't have diamonds. Thanks for the question. We do not have diamonds. Magnetite versus hematite. Kind of forget. They lift different streaks. Hematite has kind of a reddish-brownish streak, if I recall. Magnetite is, of course, magnetic. Sorry. Visceral minerals in the Titan andesite. Let's save till tomorrow, Justin. How is muscovite formed? All I can help you with, Sharon, is the same book arrangement. So I've never heard a good explanation for the conditions necessary to form basically crystals of micas. But these are the two most common mica minerals, biotite mica and muscovite mica. And there's a third called chlorite, which is kind of a greenish. Are we done idling in the driveway, sir? Could we please pull out? But I don't understand, can't find my book of mica. I don't understand how that gets set up. Here it is. Like with other minerals, you have a crystal form if you just have this huge space and you have these crystals growing towards the interior of this cavity. But is that really what we're talking about here? I don't think so, but I don't know. A few more. Do all minerals form in liquid magma? Yeah. Hot temperatures, I would visualize an underground red hot magma chamber, and as the temperature starts to decrease, you start to develop kind of a slush, like a Mr. Misty back in the day with Dairy Queen. And you see, you got solids and liquids all in there together. And I think Bowen's reaction series is what I'm shooting for here. So there's there's a certain amount of ingredients basically inside of that magma chamber, like elements, and those elements are linking up and organizing at a microscopic level, and we have different minerals forming in order of temperature decrease. So if we have a certain temperature window, a certain mineral will form, and then if we cool that off and get into a different temperature window, a different mineral will form. And there's been a lot of experimental work by Norman Bowen to figure that out. A lot of question about my favorite mineral. I assume that's from kids. We'll go with potassium feldspar, K-spar. What's the heaviest mineral discovered to date? I'm not sure that answer. Should I ask Siri right now? Siri, what's the heaviest mineral to date? She just gave me a bunch of websites. It was worth a shot. That's an old dude trick. Siri, Alexa. I don't do it that often. The Rice Museum of Rocks and Minerals in Hillsboro, Oregon. I've heard from those folks a few times recently. I've never been. I should go. I'm sure you've got a favorite museum nearby. What are we doing out there? Why do some minerals form crystals and others not? I didn't mean to give you the impression that some minerals don't form crystals. I really do mean that I don't care what mineral you are, you will grow a significant size and form crystal habit if you have enough space and you have enough time. But most of the time, like tomorrow night in an igneous rock situation, you run out of time and you run out of space and you just kind of have these kind of half-baked versions of yourself. That's a dumb way to say it, but that's the best way I can. 2 more and we're done. Aren't there way more minerals that can be found in nature than you have put on that chart? Yes, I'm not sure you heard me earlier on. We're talking about rock-forming minerals. There's, I think, more than 3,000 minerals found in nature. 3,000 minerals. You can even take a mineralogy class for a whole academic term and learn less than 50 or 60 of those minerals. But yes, there are thousands of minerals that exist in nature, and this is an hour program. Topaz is not common in rocks. So we focused on the feldspars. If you want a short list of the common minerals we're going to use again tomorrow night, the feldspars, the quartzes, biotite, hornblende, couple other things, but that's it as far as major minerals that are found in igneous rocks. Okay, if I missed your question, I'm sorry about that. But I appreciate you, those that were here and we're following along tonight. A toast to you. Again, the textbook racket is ridiculous. So I've gotten off the textbook train a long time ago because they're so expensive. But it's quite common to have lots of photos and do-it-yourself type approaches. And so if minerals are very important to you and you'd like to learn more about minerals, I'm sure there's some excellent websites that you can go to immediately, but they all have this sort of approach where you're just kind of learning by photos, learning by charts, and this is a common way to go about it, to show these different crystal shapes in illustration form, and then to show you, there's a blue mineral for you, to show you. So if this is an interest of yours, there's a lot of resources available to you that are quite easy to read and follow. You don't need tons of background. I'll show you one more. This is kind of a review of our importance of cleavage planes, angles between cleavage planes, and why those cleavage planes and angles between cleavage planes is so important. There's our halite that we broke up. That was my favorite part of tonight. Tonight was really a setup to help us make some hay tomorrow night outside. The painters are almost done, by the way, but the weather's supposed to be decent, so we'll be outside at least tomorrow night. And then sedimentary and metamorphic rocks on Thursday night, 6 p.m. Pacific time. And then we have these two programs scheduled for this coming weekend, 9 a.m. Pacific time. Here's to you and your health. Here's to the health of your parents and your grandparents, your children and your grandchildren, all the folks that you value, whether they're near or far. Here's to our health. I thank you all for joining us tonight. Hope you enjoyed it. We'll look for you tomorrow night when we talk about igneous rock identification. Good night from Ellensburg, Washington. I love you.